In this video, we applied a particle-in-a-box model for multiple electrons to linear molecules with conjugated double bonds. These molecules are called linear polyenes. Among them, the simplest is butadiene. It consists of 4 carbons and 6 hydrogens. The 3 carbon-carbon bonds consist of sigma bonds and pi bonds. The sigma bonds are localized between each pair of carbons. In contrast, the electrons in the pi bonds are free to move along the entire length of the molecule, since the pi bonds are conjugated, that is, they alternate with single bonds. In this molecule, there are 4 pi electrons. Two from each of the pi bonds. For these 4 pi electrons, the molecule can roughly be modeled as a one-dimensional box. Here is the energy level diagram of the box. Lowest level for n equals 1, then comes n equals 2, n equals 3, n equals 4, and so on. Each energy level is doubly degenerate, since the electron can be either in a spin-up or alpha state, or in a spin-down or beta state. Each one electron state is described by a wave function. For example, the wave function for an electron in the lowest alpha state is psi1 alpha. The spatial part is called an orbital. And the overall wave function for this electron is called the spin orbital. In our diagram, we have drawn separate lines for each spin orbital. Often, you see just one line representing one orbital, that is, both spin orbitals together. Now, armed with this diagram and the Pauli exclusion principle, we can put the 4 pi electrons from butadiene into the box. We are interested in the ground state, the state of lowest overall energy, so we put the electrons in one by one into the lowest available 1 electron states. The first electron goes into either psi1 alpha or psi1 beta. Either of them is fine, since they have the same energy. Let's put it in psi1 alpha. The next one goes into the other one, psi1 beta. It can't go into psi1 alpha, since then the 2 electrons would have the same state and would violate the Pauli exclusion principle. Next, the third electron goes into psi2 alpha, and the fourth electron goes into psi2 beta. The highest occupied state has quantum number n equals 2, and it's called the HOMO, the highest occupied molecular orbital. The lowest unoccupied state, which has n equals 3, is called the LUMO, the lowest unoccupied molecular orbital. We can induce a transition between states and promote an electron from one state to another one by the absorption of a photon that supplies the right amount of energy to bridge the energy gap. This change of state is called an electronic transition, that is, a transition involving an electron. The electronic transition with the smallest amount of photon energy needed is the one from the HOMO to the LUMO. The energy difference in our case of butadiene between these two states is given by delta E equals E3 minus E2 equals h squared over 8ma squared times 3 squared minus 2 squared, which simplifies to 5h squared over 8ma squared. For butadiene, the approximate box length A is about 400 picometers. This gives an energy gap delta E of about 1.88 times 10 to the negative 18 joule. To induce a transition between these two states, an incoming photon must therefore deliver this amount of energy. Formally, the energy of the photon must be, which equals to h nu, or in terms of wavelength, hc over lambda, has to be equal to delta E. From this, we get lambda is approximately 106 nanometers, which lies in the UV range. This is indeed where the molecule absorbs experimentally. Our quantum model is successful in predicting the absorption spectrum of a molecule. This model is called the FEMO model. The FEMO is an abbreviation that stands for the free electron molecular orbital. It's important to realize that this very simple model is a very crude approximation. We've made the following simplifications. First, we restricted ourselves to pi electrons only. Of course, this is a simplification because there are many more sigma electrons. Second, we assumed that the potential energy is flat within the box. V of x equals 0 inside. In reality, there are periodically spaced, positively charged carbon nuclei, so that the negative electrons experience different Coulombic attraction depending on their position. The third approximation was that we assumed that the walls of the box are infinitely high, essentially at V of x equals plus infinity outside of the box. Again, this is an oversimplification. It's not the case in reality. Fourth, we've assumed the electrons are independent. This is a gross oversimplification, because clearly two electrons repel each other due to their negative charges. That means that position and momentum of electrons are usually correlated. This electron correlation is neglected in this model. Despite these almost irresponsible simplifications, this quantum model gives results that are surprisingly close to experiment.